So today's video will be divided into two parts. Now the first part will be me sharing my thoughts on the topic, does measurement matter? And the second part will be a recorded conversation between me and Harley. Now Harley is the speaker designer for the Sibelius speaker designer. Now for those of you who have not seen my video on the Sibelius speaker, please go check it out. Now given today's video will be quite long, I'll get straight to the point. As an analyst for over a decade, I learned to be very specific in how I ask questions. Does measurement matter? For me, it's an incomplete question. Let me explain. Think about it this way. Does measurement matter to understand why I'm hearing what I'm hearing? Does measurement matter when designing a speaker? Does measurement matter when making a decision on what DAC to buy? See, although all the questions start with does measurement matter, the answer to each question is not the same. I would answer yes to the first two questions, but no to the last one. Why? Now, as you know, SMSL products are known to measure really well. Take any of the DAC and AM, and usually they get a passing grade on the website Audio Science Review. There is, however, one DAC, the SMSL R2R D3 DAC, that did not measure well. And yet, out of all the SMSL products I've tried, that is the only SMSL product I bought with my own money after trying it. So measurements are not that important to me specifically. Now, having said that, I do respect anyone who makes their buying decision based on measurements. Now, as for Audio Science Review, yeah, I respect Amir for being consistent. If it does not measure well, he does not recommend it, period. So that is where I stand regarding measurements. Now with my conversation with Harley was like almost an hour. So I've decided to cut out certain parts, and you know what? I might even split the video into two episodes. Now we talked about number one, measurements. Number two, how is it possible to get so much bass from the Sibelius? And number three, his recommendation on how to choose a speaker if you cannot audition it. So let's transition to the second part. And guys, forgive me, we recorded the call, but it was recorded in low quality. So the video looks like it was streamed from the International Space Station. All right, guys, it's Thomas here. So I have Harley, the designer of the Sibelius speaker here today. And the reason I'm chatting with him is because partially I have a question myself. Now, I figure I'll record this call so I can share with you guys what we discuss, because it'll be on a topic that's a bit controversial, measurements. Right now, before we begin, I'm going to let Harley introduce himself. So think of this as a job interview. Give me your CV, Harley.
Well, thank you for inviting me onto this recording, Thomas. I really appreciate it. I think someone should may want to get to know me a little bit because of the fact that since as I was a child, I was passionate about music and recorded music. And since I had my first wind-up gramophone, which my dad bought me from a second-hand shop in the 60s in London, I've always made this incredible link between the recorded sound and music. And in fact, I didn't even realize it was more or less humans making music until I was quite a bit older, because it was just magic that came out of this box. And from that beginning, probably became a lifelong passion into building equipment, how do amplifiers work, looking at those, and then designing and making my own loudspeakers, mainly in the beginning because I had no money and I just enjoyed, compiling and making things together and working out how things work and having a very inquiring mind. And then over the years, it became a passion that got out of hand. So it had to be converted into a business, into a VAT number. And here we are today, selling our products all over the world.
I see. And I understand that you're also into recording, right?
Yes, very, very much. I do a lot of classical recording, only acoustic instruments, classical music these days. And that is, it's just getting that close to the actual acoustic instruments. And that's really the passion. It's from the microphone to the living room. That is what really excites me. Yes.
So right now I'm facing a problem. Okay. As you know, I'm bringing an amplifier to market. I'm also actually bringing a speaker to market. And one of the problem I'm facing is the designer of the amplifier asked me. You see, I asked him to adjust certain things because I like the sound better that way. And he came back with, can we compromise? Meaning that half of it, yes, that's settings. I'll do what you asked me. But the other settings, because my amp can choose between musical and analytical. So for analytical, yes, I will do what you want, Thomas. But for musical side, I suggest that we go with my setting because it measures the best. Now, I've heard it before. It sounds good, but it just does not sound as good as the analytical side in terms of openness. So that's why I'm debating, should I go with what measures well, or should I just go with what my ear tell me? That's number one. The second thing, when I was talking to my speaker designer, he told me straight out in the beginning, he's been designing speakers for 30 years. And he told me very specifically, your speaker will not measure flat. It will, he would voice it by ear at the very end, and it will have these funny peaks and valleys. But he's been designing speakers that are like $10, $20, $30,000. So, he has experience. I guess so. My question to you is, what is your thoughts about it? This measurement versus, what we hear. All yours.
Okay, it's a very interesting question. The whole topic of specifications is a complex one, because on the one side, my logical brain is saying specifications matter. So the first thing when I see a review in a magazine or hear about a piece of equipment, I go bang, straight to the specifications sheet. I'm looking at how many watts per channel, what's the distortion figures at 1 kilohertz, and those are all those things. But I also know that it's meaningless. So I'm sorry to say this, but both things are correct. So when you are designing and making things, what you want is your design to be under control, meaning you think something up and you want it to be as you thought it up. So in order to do that, we need to measure, and we have certain expectations. We would expect that your new amplifier, for example, would be able to reproduce all the notes of a symphony orchestra or a rock band. So it should be able to go from, should we say, 20,000 hertz at the top to 220 hertz at the bottom. And although most of the time we are listening to a much narrower bandwidth in reality, we would expect that, okay? Now, the best analogy I can give you is in the recording studio. I go to record a few musicians. Let's assume, just for sake, if it's a piano and a cello, for example. And I can choose, I can open my box of microphones and I choose the right microphone, the one that I like for this circumstance. But I could choose a Brüel and Kjær test microphone, because Brüel and Kjær are famous for their microphone manufacturing, and they specialize in test microphones, and they are exact. From 20 hertz to 20,000 hertz, exact, plus or minus 0.1, whatever the limitations of microphone design are, that's where they take it to. But if I recorded the piano and cello using those microphones, I would never get asked to record again, because there's something about a microphone. And I will share with you a graph from one of my microphones. I like using AKGs a lot. They've been around for 40 odd years. I like using them. But if you look at the graph, there's a little bump around 6,000 hertz. Now, they do have a version which is less, but all microphones have their own characteristic, just like your amplifier, just like your loudspeakers. And I know when I'm walking into a space, a recording studio, a space, a church, wherever it's going to take place, and I'm listening to a violin and I think, oh, that violin's quite harsh. It's got quite a harsh sound, that wood or the bow has got a lot of rosin on it. You know what? I'm going to use this microphone or that microphone because I know what it's going to sound like at the end. My experience has taught me. So in that sense, specifications are important. But at the end of the day, your loudspeaker designer is completely right, because when someone says, oh, this amplifier's got a warm sound or a hard sound or a soft sound, or the mid-range, the voices are very forward, they're in front of your speakers, or they're back in the mix. It's a wide sound stage. Most of the time, what we're talking about is a frequency response. If I'm in the recording studio in post-production and the violinist is playing, or there's a singer, I've just recorded a trio. If we want Maria, the soprano, to come forward, we can actually, my engineers will just tweak around about 1,000 hertz, 1,500, drop some other frequencies back around her, and she will physically move forward or backwards in the mix. Now, it's a little bit more complicated. I've oversimplified, but basically that's what we're doing. So a loudspeaker, probably the most famous loudspeaker of all time, is probably the little LS35A. It is anything but flat. But the BBC engineers, when they were designing that, they wanted something small that will go into their outside broadcast vehicles, but they wanted something that sounded like the best radio at home. So if it sounded good on that, it would sound like it should be at home. So this is really what we're talking about. And there's quite a big peak around about 100 hertz in that loudspeaker. It's anything but flat. So what I'm doing is, yes, I'm applying science. So when Mark Fenlon designed the drive cone for our loudspeaker, and that drive cone is very much like a microphone in reverse. In fact, it's exactly the same principle. Mm-hmm. There were about 9 parameters. I won't go through them all that we took into account. Like one of them is Q, QES. These are figures that are giving us indications about how the tube or how the cabinet should be constructed, what the physical resistance will be of that drive cone. Lots of things are coming into account. Yes, I'm taking into account all of those, but there comes a time when you have to stop and actually you build your enclosure and then you use your ears and then you invite the person you really don't like very much, but is an audiophile and has a completely different view on life than you do, listens to different kind of music from you do, who's not afraid to say, Harley, that sucks. And you invite them and you invite other people. And in our case, we went out for about 18 months, 2 years. The whole process took of demonstrating our loudspeakers in various formats, giving people evaluation forms to fill in, which are confidential, and listening again and checking again. And at a certain point, I remember a good friend of mine, Erwin, a very, very experienced guy who'd been working in loudspeaker design for decades. He said, Harley, stop. You know, stop, you've got it now. That's it, leave it alone. Because we could only change things by changing the height, the depth, the width of the cabinet, or tuning the cabinet with various ways, because it's a physical wooden construction. We don't have a crossover or anything else. So in conventional loudspeakers, you can settle on your cabinet design, you can settle on your drive cones, and you can tweak them by changing a capacitor or an inductor or a resistor in the crossover, and that will make a dramatic difference. And you can impact the phasing and all sorts of things. But so your testing is important. And when I was much younger, designing in my heyday at 1985, around that period, my brother and I, you know, we were using oscilloscopes and watching the curves of our crossover designs, and they were very complex. I mean, sometimes we had like 30 components on this board and we wanted it exactly flat, and you built this perfect enclosure, and it just sounded rubbish, you know, it just sounded awful. And then we started pulling off components until it started to sound nice. The other point is that really specifications only make sense, especially with loudspeakers, in an anechoic chamber, a room with absolutely no echo. I don't know if you've ever stood in one of these rooms, but it's a really unpleasant experience. It's horrible. You can't spend more than 10 minutes in there. It's a very strange environment. So no one has an environment like that. So the problem is that your room is going to have a very big impact on the overall sound. The good news is that human brains adapt to what is normal very quickly. So if you've got a very echoey room and it's very hard, probably your brain will adapt to it and it will very quickly become normal. But it is also important then in your design, especially when you bring out your loudspeaker, to listen to it in lots of different locations. You know, take all the furniture out of your room, pull up the carpets, take away the rugs, play heavy metal or whatever it is and different things in there. Go to your friend's house with a heavy damp room, because actually you're trying to find a product that will work as good as possible in a variety of environments. And
So
it is difficult.
So I guess the question is that, you know, let's say the speaker measure with a big dip problem, like a big, right? By textbook case, it is bad. For example, the Clip Sharpie 600M, if you measure it close enough, I mean, there's a big dip, but it sounds great. So then what do I do? I mean, if I get this speaker and I see a big dip in the measurements, but it sounds great, do I correct it? Like, I'm not okay. For those of you who are watching, okay, I'm not trying to pick a fight with anybody here, right? But I am about to bring a speaker to market too. And this is a question a dilemma I'm facing. If I see a big dip, do I ask them to correct it, despite if I hear and it sounds fantastic?
Be very careful, Thomas, because your designer's got 30 years of experience.
More.
And just because you see a dip doesn't mean it's wrong. Okay. What I would say to you is, when you're listening to music through your loudspeakers in your room and in a couple of other rooms, just pick like 2 or 3, otherwise you'll go mad. And listen to pieces of music that you really know and you're familiar with, and different types, and listen to it and ask yourself, does this sound right? Is this nice? Is it pleasant? Am I enjoying this? Another thing you can do is listen to the beginning of Sibelius's 7th Symphony, for example, because it begins with the scale of C and the orchestra is going up the scale, da, 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 da. It's his last symphony. I don't know why he started it with a very simple scale. And if you suddenly hear that certain notes are sounding much louder than another, if when you're listening to your favorite jazz piece, ever so often the double bass goes boom, 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 always on the same note, then you can look at that graph, check to make sure it's not the room, because if you've never had that before, then there's probably something wrong with the loudspeaker design. And you'll see that there's a blip at some point, and then you would want to correct it because it's annoying and it was not there with the other speakers you've been listening to. If on the other hand, it's not there and it's not annoying and everything else sounds right, and you give it to your friends and you've got all your famous selection of friends who studied in detail our loudspeakers, if they're all giving you the thumbs up, it's okay, because there's no violin maker or cello maker or piano maker or flute maker or guitar maker that I know of who goes into an anechoic chamber with an oscilloscope and makes sure that everything is flat. It just doesn't happen. And I'm going to bring, so I hope, so if you hear a repetitive noise or a repetitive syndrome across all your recordings that keeps coming back and it's annoying, you don't like it, even with different amplifiers, you know you've got a design fault. And generally you know it immediately.
Okay. That's definitely a good idea there.
Sorry, I felt I'm beating you up here.
No, not at all. Not at all. And as I said, guys, I know that when I mentioned about the Clip Sharpie 600M, a lot of you might think of GR research, right? As I said, this is really not picking a fight. Over the years, I get a lot of emails from my subscriber, and I have subscribers sending me emails saying that they did the modification and it sounded bad. And then I get emails also, subscribers sending me, man, this is the real thing, man. You should buy a speaker modified with GR research stuff. It sounds fantastic. So I get emails from both sides. So that's why I'm like, okay, should I try to ask my designer to aim for that flat curve, or forget it, man? Just listen.
Forget it, Thomas. Forget it. Relax, sit back, enjoy the show. Let your designer work.
Now, not to ask you to divulge any information or secrets. So if you're telling me if I measure the Sibelius response graph, it's not
it won't be flat. No, it's not going to be flat. Oh my God, no. And it will be different if it's 1 meter away from the wall or 1 meter 20 away, or back against the wall or to the left, or if you move your plant to the right slightly and you twist it. You know, where it moves in a room is incredible. When you do some testing, which is great fun to do, get yourself a test microphone, set up some testing, you know, there's some great kits on the market. What you will notice is that when you move the microphone literally 8 inches, 8 inches from to left or right, you can get a completely different result. It's so weird, and you can move forward or backwards, because what happens is that there are nodes appearing, and the way that the sound is bouncing around your room, the most incredible things. You must have noticed it. Sometimes there's a certain point you stand in your room and there's a hell of a lot of bass when you're in that room, and you can move just a few inches to the left or right and it's gone.
Yeah, for sure. So, that bass thing there, it depends where you stand. Yeah, absolutely.
So if you want to measure the Sibelius loudspeakers, rent yourself an anechoic chamber, go in there, and get yourself a decent Broyle and Kira microphone, and then send me the result, and I'll ignore it. I mean, because at the end of the day, our customers are very happy, and your team were very happy with them, and I would be a fool to try and change them. It would be very easy to make a kit that you could plug in to make everything perfect. We use Yamaha HS7s when we're doing playback in recording environments, because there's always different environments. And music sounds, I know to be rude to Yamaha, but on those it sounds horrible. It's not pleasant experience, but we hear every single detail. And if there's a noise in the studio or a musician is not quite in tune, we will hear it there. And that's exactly what they've got to do, is to reveal everything. But I wouldn't come home and listen to music on them, right? Sorry, Yamaha, but they're not designed for that. They're studio monitors. So don't build a monitor, build a pair of speakers. Are they going to be small or big, or is that a secret?
No, it's a bookshelf. It's
lovely.
Yeah, two-way, right? So
lovely.
All right, so let's move on to the second point. Now, when I first got the Sibelius from you, you see your whole marketing idea. Well, one of the selling points of the Sibelius is that it reproduces musical instrument as accurate as possible, right?
Yeah.
And the big question I had before I received it is, how is that little driver going to handle double bass? I mean, these things go very low, and bass with all the single driver I listened to sounds a bit lacking, except one or two, but those were $10,000 speakers with gigantic cabinets. I guess I'll let you take the time to explain it to me. Like, should my speaker report it, or should it be sealed? I guess maybe I'll throw that in.
Okay.
No.
What do you want me to deal with first? I mean, okay, so, I mean, I knew you were going to ask me this question.
Yes.
How does this little 4-inch drive cone create so much bass? And it is the first thing that everybody goes, oh, wow, you know, because it's just thunderous. I mean, there's no lacking in this bass, and people think, well, how does it happen? They're looking for sort of an 8-inch driver hidden inside somewhere. And what is going to be shocking for you, some of your audience, and they won't believe me, and you might get a few rude comments, but there is no direct relationship between the size of a drive cone and how deep or how much bass is produced. It's now, if you just think about it, there are subwoofers, and I'm thinking, like, my daughter's got one from Yamaha, and then I remember we had in our cinema room a little Bowers and Wilkins one. It wasn't very big. The drive cone was quite small, and that used to produce thunderous bass. But we've got so used to this imagination at a concert where there's a big cone and it's going to produce lots of bass. No, it's going to move a lot of air if it can move forwards and backwards, but it has no correlation with bass. Let me give you a very simple explanation. I was at a concert just last night, and a friend of mine, Balder, was playing oboe, and his brother plays bassoon, right? And a bassoon is like a big oboe, right? And a bassoon can go very, very deep, very, very low notes, okay? But I'm going to show you something. See this little thing here? This here, can you see that?
Yep,
This is a pair of reeds from an oboe. Now, you can see how big it is. I've got small fingers and it's tiny. Now, the bassoon's reeds are very slightly wider, so they're no wider than my little finger, but that's it, right?
Mhm.
Now, when they blow those together in their mouth,
Mhm.
this is connected to a pipe.
Yeah.
And the bassoon's pipe is, I've never measured one, but I guess it's about 1.25 meters. It's about 3.5, 4 feet, right?
Mhm.
From this tiny little thing, it's that thing vibrating that's creating the note. Whether it's high or low, it's this that's vibrating that creates a note. And that goes into the pipe, down the pipe. And these tiny little things will produce a bass note so low and so loud, you will hear it right at the back of a symphony hall orchestra, even when the orchestra is playing. So this correlation between getting a vibration and a low note is what makes it. And instead of this tiny little thing, I've got 4 inches or more. It's a little bit more than 4 inches, actually, but more in 4 inches moving, and it can move 6 to 8 millimeters in each direction. This is just moving a fraction of a millimeter. So actually, it's the ability for that cone not to bend, not to twist, not to lose its energy, and push and vibrate at the right frequency. And you put that over the pipe. And our cabinets, as you know, like they're thick oak, like 1.5 inches thick, 3.3 centimeters. I don't quite know what that is in inches, sorry, but it's over an inch thick. And it's this tight pipe, and it's creating the sound. Same thing when you were a student, pick up a small glass beer bottle and blow across the top and hear how low the note is that's coming out. This is what we're doing. That's all what we're doing. It's basic acoustics.
If that's the case, then how come some speakers, despite having a port also, cannot go very low? Because it's still moving a lot of, right?
Oh, that's a good question. Why can't they go very low? Okay, because because the enclosure they're in is very small.
Okay.
Right.
Yeah.
And it hasn't, and the wavelength, because we call ours quarter wavelength, hasn't got a chance to form inside the cabinet. So all you can do is rely on that movement of the cone itself. Then a bigger cone can help. An 8-inch rather than a 5-inch can help a little bit, because you're relying just on the sound of what's coming from the cone. You can't rely on the cabinet. And therefore, what you do is you use a crossover to hold all the loud notes, all the 1,000 hertz, the voice, all the rest, to hold it all back until the bass sound that drive cone is making is equal to or similar to the rest of the spectrum, within which it's designed to work. So when you've got a bass speaker, a bigger speaker in a 2-way or 3-way, actually what you're doing is holding back all the rest until the bass is loud enough. And that's why most bookshelves have a low efficiency, 83, 85, 87. Look at any bookshelf where it's not active, of course, right? And you've got quite a low roll off. I mean, sometimes, I shouldn't say it, but sometimes some manufacturers exaggerate what the roll off. When you look at the specifications, they go 40 hertz. And you look at the design and say, yeah, that's impossible. Theoretically. So what they're doing is they're holding back with resistors and capacitors and inductors, making these crossovers to just use the natural ability of that bass driver to push the air. But we're not using, the cone is just creating that frequency, just like these reeds from a bassoon. And it's the enclosure making the thing. Now, why a lot of people don't like single driver loudspeakers or this kind of design is because the enclosures have to be quite big. And in order for economy and size, they're often made of thin wood and it's not braced. And so the wood itself is rattling, not rattling, that's unfair, but it's making a lot of noise of its own and adding a lot of color. But we've managed to avoid all that color by just using the same technology as an organ pipe from a church, and the same technology and approach as a double bass or a cello or whatever. So that's kind of the thing. So your 2-ways and your 3-ways are relying on the cones to make the noise rather than push the air through a column.
I see. So in my case, in my speaker, the cone selection will have a more important
No,
factor.
less important because you can, any failing within the cone,
Yes.
you can correct in the crossover or in the cabinet
Oh.
design. You can really, that's the beauty of you being able to use crossovers. You can really design the filters. They're filters, in fact, however you want, and make sure the phasing's right. For us, we didn't have any choice. We've just got these reeds. And the interesting thing about these reeds is if you change the wood, if you watch an oboe player, a bassoon player, when you see them come onto the stage, they'll have a little box about this big. And when you open it, it's full of these. And they will pick them up and they make them themselves because it's the only way to get it reliable. So they cut the wood with a sharp knife and they make them and they wind them all together like you can see here. And one will sound a lot better than another. One will sound more warm, one will sound more harsh, one will start squealing. And they will switch and swap these things until they get the sound they want for the piece of music they're playing. This is a bit like my single drive cone, but you can do all this electronically in a two-way. You can just add a 5 microfarad capacitor, put it over an inductor with a resistor, and hey, you've got yourself a nice little filter.
I see. Okay, that's fascinating. Wow. Okay, so I guess, yeah, that's very exciting.
Next time I mean, when you're a kid and you had the pipe of the vacuum cleaner or something, you swing it around in the air and you get a very low sound. That's what we're creating. It's what we're doing. It's how a musical instrument works. Think bassoon, and you'll see that it's not a miracle. There's nothing clever about it. It's age old. It's laws of physics.
All right, Harley, so let's wrap it up at this point. All right, I will end the video at this point and we'll share the rest of the interview in a future video. Now, I hope you enjoyed it and thank you for hanging out with us. Till next time.